Today on Quickly Quantum, quantum machine learning's founding promise that entanglement, the spooky link between particles Einstein distrusted, hands quantum learners an exponential speedup over classical ones, just took a serious hit from a new paper out of KAIST. The question we're spending the whole show on, was entanglement equals advantage ever actually true? Or did the field build a decade of hype on a proof that only works in the idealized case? No headlines today. This is our Sunday think piece, one subject top to bottom, because this fight has been simmering since 2018, and it just got a lot more interesting. Welcome back to Quickly Quantum, your daily brief on the quantum frontier. It's Sunday, August 16, 2026. Let's get into it. Here's the tension this whole episode lives in. For about a decade, quantum machine learning, using a quantum computer to spot patterns in data, the same job a neural network does, just on different hardware, has been sold on one core claim: entanglement, the correlation between qubits that lets them behave as a single system no matter the distance between them, is the resource that lets a quantum learner beat a classical one, sometimes exponentially. And exponential is not a marketing word here. It means the classical machine needs a number of samples that scales like 2 raised to the number of qubits, while the quantum one needs something closer to just the number of qubits. And once you're past a few dozen, that's the gap between solvable and never finishing. But that claim has taken hits before. Back in 2018, Yuan Tang, an 18-year-old who just finished her bachelor's degrees in computer science and math at UT Austin, before she'd even started her PhD at the University of Washington, dequantized the quantum recommendation algorithm as her senior honors thesis, meaning she found a classical algorithm that matched its performance with only a polynomial slowdown, not an exponential one. That single result kicked off a wave of copycat dequantizations across quantum machine learning, repeatedly showing that celebrated exponential speedups depended on assumptions about how you access data, things like QRAM, a hypothetical quantum memory, that turned out to have classical workarounds nobody had bothered to look for. So the field has spent years oscillating. Prove an advantage, watch someone dequantize it. Prove a narrower advantage, repeat. Now add one more wrinkle that most casual coverage skips entirely. Entanglement itself isn't one thing. There's free entanglement, which you can purify into clean, maximally entangled pairs through local processing. And there's bound entanglement, states that are genuinely, provably entangled. They fail the standard test for being separable, but no amount of local squeezing ever turns them into that clean, useful form. Bound entanglement has always been quantum information's odd cousin, real, but historically useless for the flashy applications, like teleportation, that made entanglement famous in the first place. This week, a KAIST team asked the obvious next question about that odd cousin. If entanglement generically is supposed to power quantum learning's exponential edge, does the bound kind still deliver it? Their answer reopens the whole fault line, and it lands at a moment when quantum AI is showing up in funding decks with a lot less nuance than the actual math supports. Our named thesis today, borrowed straight from the paper, not all entanglement is created equal for learning speedups. The KAIST team restricted either the input states or the measurement effects, the operations you're allowed to perform on the system, to satisfy something called the reduction criterion, a mathematical condition that every bound entangled state happens to obey. Under that restriction, for what the paper calls incoherent adaptive protocols, learning strategies that update their approach step by step but don't hold long-term quantum coercion across the whole process, the exponential sample advantage completely disappears. It's gone. Classical and quantum learners end up needing comparable numbers of samples. There's a nuance worth keeping, though, because the paper isn't a blanket entanglement doesn't help result. For one-sided coherent adaptive protocols, a stronger class of strategy that does hold coherence, the team says an exponential lower bound persists, meaning bound entanglement still can't be ruled out as useless there. And using a tool called conditional min entropy, a way of measuring how much genuinely unpredictable quantum information is locked in a state, they quantified something subtler than a yes or no answer. The sample complexity lower bound weakens gradually as a state's violation of the reduction criterion gets more severe. In plain terms, the closer a bound entangled state sits to behaving like an unentangled one by that specific measure, the less learning advantage it can offer. It's a dial, not a switch. The headline takeaway from KAIST is narrower than entanglement is fake and more useful for it. The resource that actually matters for exponential learning advantage is a specific quantifiable violation of the reduction criterion, not entanglement in general. That's a real distinction with teeth, because it means two states can both be legitimately, provably entangled, pass every test physicists use to certify entanglement, and still land on opposite sides of whether they can speed up a learning algorithm. If your funding pitch says, "Our system uses entangled qubits, therefore it learns faster," this paper is the reviewer note asking which kind of entangled and how much. None of this means the advantage camp is out of ammunition, and it's worth being fair to them because their result is a theorem, not a hope. Back in 2021, Xinyuan Huang, Richard Kung, and John Preskill proved that entanglement between a quantum system and an ancillary quantum memory, extra qubits you use purely for bookkeeping, not for storing the answer, can produce genuine, provable exponential separations in sample complexity for learning quantum states and channels. Google's team went further and actually ran it. They demonstrated a power of data advantage on real quantum hardware, not just on paper. A follow-up study out of KAIST itself pushed that further with a concrete example: learning properties of a bosonic continuous variable system. Think of it as a quantum system described by continuous values rather than discrete qubit states, like light in an optical mode. Without entangling the modes to an ancillary memory, you need to sample the channel an exponential number of times. With a simple entanglement-assisted scheme, you need a number of samples that's independent of the system size, n. That's about as clean an exponential separation as this field produces. Then, a further group of theorists asked the sharper engineering question: how much entanglement do you actually need to get that speedup? Their answer, distinguishing entanglement from ancilla-qubits as genuinely separate resources, is that a vanishingly small amount of entanglement in the input state is already enough to learn a type of quantum channel called a polychannel with only a polynomial number of queries. But, and this is the part that should reorient how engineers think about near-term hardware, without a sufficient number of ancilla-qubits, even learning partial information about the channel costs an exponentially large sample size, no matter how entangled your input is. So the scarce resource on real devices might not be entanglement at all. It might be spare qubits to use as scratch memory, which changes what a hardware roadmap should actually be optimizing for. Zoom out though, and there's an entirely separate skeptical tradition that predates this week's paper by close to a decade, and it's worth putting it back on the table because it's the pattern this new result rhymes with. That 2018 dequantization I mentioned, Yuan Tang showing a classical algorithm could match the quantum recommendation algorithm with only a polynomial slowdown, wasn't a one-off. It kicked off a wave of copycat results across quantum machine learning, and the pattern each time was nearly identical. An algorithm gets published with a headline, exponential speedup. Then someone goes back and finds that the speedup only shows up if you grant the quantum algorithm privileged data access, something like QRAM, a hypothetical fast quantum memory for classical data. And once you give the classical algorithm equivalent sampling access to the same data, the exponential gap collapses down to polynomial. The uncomfortable question that history poses for this week's KAIST result is simple. Does dequantization eventually eat every claimed exponential QML advantage, the way it ate quantum recommendation systems? There's a real argument that it might not, at least not everywhere. The tasks Huang-Kueng-Preskill and the ancilla-qubit work are about. Learning properties of an actual quantum state or channel require physical access to a quantum process you're trying to characterize. You can't dequantize your way around not having the quantum system in front of you the way you can dequantize your way around a classical dataset sitting in a matrix. That's a structurally different setup than quantum recommendation, where the underlying object being learned was classical data all along. So dequantization probably isn't a universal solvent for QML claims, but it is a standing challenge that any new exponential advantage paper needs to answer before the field takes the result as settled. What exactly is the classical algorithm not allowed to do here? And is that restriction physically meaningful, or just a modeling convenience nobody stress tested yet? And then there's a broader objection that doesn't even engage with the entanglement math. It questions whether does quantum beat classical is the right question at all. Maria Schuld and Nathan Killoran at Xanadu have argued that machine learning gets listed as one of quantum computing's most promising applications, and they call that a curious choice, because today's classical machine learning algorithms are notoriously powerful in practice while remaining theoretically difficult to fully understand. Nobody has a clean proof of why deep learning works as well as it does. Quantum computing, meanwhile, doesn't yet offer practical benchmarks at any realistic scale, which leaves theory as basically the only tool available to judge whether QML is relevant at all. Their conclusion? That's a shaky foundation for a field-defining advantage narrative, and they've explicitly called for a critical debate on whether beating classical machine learning should keep dominating the literature the way it currently does. Scott Aaronson comes at it from the hardware side, and he's characteristically blunt about it. On his blog, he's warned of what he called a tsunami of hype about what quantum computers are going to revolutionize, and argued that quantum computing has effectively turned into a word sprinkled onto funding pitches. His point isn't that the theorems are wrong. It's that even granting every exponential advantage proof in this episode, practical QML speedups depend on fragile assumptions. QRAM, low rank or well-conditioned data, noise-free operation, none of which hold on the noisy, error-prone quantum processors actually sitting in labs today. We can't be certain, he argues, that these machines will in fact revolutionize machine learning, finance, or optimization the way the pitch decks imply. Put Schuld, Killoran, and Aaronson together, and you get a consistent through line. Even if the KAIST result, the Huang-Kueng-Preskill theorem, and the ancilla-qubit refinement all hold up perfectly on paper, that's a separate question from whether any of it matters on a NISQ-era chip today, or whether quantum versus classical was ever the framing that should have driven the field's priorities. So where do I land on all this? I think the KAIST paper earns its narrow scope, and that's not a knock. Precision is the point here, not a weakness. It doesn't kill the idea that entanglement powers quantum learning advantages. The Huang-Kueng-Preskill theorem still stands. Google still ran it on real hardware, and the ancilla-qubit follow-up still shows a clean exponential separation for a specific channel learning task. What KAIST did is take a sledgehammer to the sloppy shorthand, entanglement equals advantage, and show that shorthand was always doing more work than the math actually supports. The right resource, at least for the incoherent adaptive protocols they studied, is a specific, quantifiable violation of a criterion most people have never heard of, not entanglement as a category. That finding tells engineers exactly what to measure instead of waving at a Bell inequality violation and calling it a day. A more useful answer than simply declaring entanglement doesn't matter. Here's the part that actually matters for the machines people are building right now, not just the theorems. Bound entanglement-like states, messy, imperfect, hard to purify correlations, are exactly the kind of thing noise tends to produce on real quantum processors. If a chip is noisy enough that its entanglement looks more bound than free, and this week's result says bound entanglement structurally can't deliver the exponential learning speedup in the regime they tested, that's a genuine warning for anyone claiming a near-term quantum AI advantage on current hardware. It doesn't touch error correction directly, and it's not a networking result, but it does say that the idealized entanglement assumed in most quantum advantage proofs and the messy entanglement noisy processors actually produce may simply be different objects, and closing that gap could matter more than adding qubits. The open questions the field hasn't answered. Is there a clean, general rule for which entanglement properties are necessary and sufficient for exponential advantage, or does the answer stay task-specific forever? Does the dequantization pattern eventually reach channel learning and state learning tasks too, the way it ate quantum recommendation systems, or are those tasks structurally protected because they require physical access to a quantum process rather than a classical dataset? Nobody in this episode's sources has closed either question. Time for the hype check. I'm not slapping a clean number on this one, because the honest scorecard cuts two ways. On substance, this is about as real as it gets. Peer-reviewed grade math that narrows a sloppy claim the industry leans on constantly. On real-world stakes, it's still theory. Nobody's run this on an actual noisy processor yet to confirm the bound entanglement warning translates into a real-world result. The next real test isn't a fresh theorem. It's somebody actually measuring the reduction criterion on a noisy processor and publishing what falls out. And that result, whichever way it lands, will tell us if bound entanglement's weakness is a lab curiosity or the hardware's daily reality. If a story like this, the kind that rewards patience instead of headlines, is the reason you listen, follow Quickly Quantum wherever you get your podcasts. And if you've got a minute, send it to the one friend who keeps asking you what quantum computing actually does. This has been Quickly Quantum, an AI-voiced podcast, created and built by a real human using today's cutting-edge technology. Nothing you heard on this show is financial advice. I'm Brian Lampert, and I'll catch you all tomorrow. Take care.